Okay, good morning. It's a pleasure to welcome to the IAC Professor Eline Tolstoy. She's a well-known expert in Europe in the study of stellar populations and the evolution of galaxies from its fossil record. Eline did her PhD at the University of Groningen, finished in '95. Then she worked on the with an ESA fellowship at the European Coordinating Facility of the Space Telescope. After that, 2 years at ESO. Then 1 year at the UK Gemini Support Group in Oxford. And in 2001, she went back to Groningen with a fellowship from the Royal Dutch Academy of Arts and Science. And after that, she got a permanent position in Groningen. And she's full professor since 2011. Okay. Welcome.
Thank you very much. Thank you. It's a real pleasure to be here at the IAC. I'm very unused to giving talks in front of expert audiences, I have to say. You have a very nice mix of people here at the IAC who work on stellar populations. And quite a lot of what I do has a basis here. And a lot of people here have been working very hard on especially aspects of star formation history determinations. And I hope it comes clear in my slides. I usually try to acknowledge the fact that a lot of work has been done here, and I would like to acknowledge it also now. You may realize that I'm starting my talk a little bit more in a general way, because I'm presuming that not everybody is familiar with this kind of work. So how fast I go through the introduction depends a little bit about how quickly you fall asleep, and we'll see how it goes. And I'll try not to lose my headgear while I'm talking. So I should first explain my title a little bit. It was a little bit an attempt to be somewhat alternative. A lot of times people call this galactic archaeology, but I actually think the analogy is a little bit more with fossils, because we talk about the fossil record, and so correctly we should use the term paleontology. So I use this example of a fossil fish with a fish inside to represent something like a life form that died out a long time ago, but we understand something about its properties by looking at how the fossil behavior of the system. And just to drive the point home, it looks something like this. You have the old ancient fossil and the modern fish, and trying to understand exactly the link between what happened in the past, what happened now, what has changed between the past and behavior that you see now is exactly what you can see in galaxies. So when you look at an elliptical galaxy, such as this one, you're looking at an old system. And you presume this old system has signs, sometimes obvious, sometimes not so obvious. It's very rare to find a fossil with such an obvious sign of having eaten a smaller fish. But sometimes you do see that in elliptical galaxies. And of course, when you look at massively star-forming galaxies today, like M82, you're seeing signs of life today. What is actually happening? What is the evolution of a galaxy today? And we really want to understand how these different systems relate to each other. So when you look at ancient star formation, and we do think that most star formation in the universe occurred a long time ago, so we really have to try to understand what is the connection between what the properties of galaxies are that we see today and what has actually been happening in the past, and what is the link. And this allows us to make a link between stars and star formation and cosmology, and what happened in the early universe and how galaxies first started to form and evolve. Before I really start, I should also pay tribute to my colleagues. A lot of work that I've been doing has been done within the DART team. We're mostly doing spectroscopy of individual stars, and a number of people have contributed a lot to the work that I will present throughout the talk, especially Giuseppina Battaglia, who just joined the IAC quite recently, so now we have a member at the IAC, which is very nice indeed. And a number of PhD students like Auza Skuladotter, whose work I will try to cover a little bit at the end. But broadly speaking, I'm going to talk about how we do our work. So what is the way in which stars enable us to carry out this kind of paleontological study? And the first most important thing is that stars actually have well-defined and well-understood useful properties that allow us to trace back, to look at what happened in the early universe. Because stars live a very long time, and because their cooler outer photosphere is actually able to absorb light from the center of the star to create absorption lines, which allow us to measure metallicities, to measure colors, and to say something about this outer photosphere, which is believed to be unchanged by the long evolution of a star, especially a main sequence star. It sits there for many giga-years, many billions of years, and doesn't evolve very much, but it carries around this outer shell, which is representative of what the properties are of the gas out of which the star originally formed many billions of years ago. So they are probes if you can find them, of the earliest star formation that you'll find in the universe. And it's interesting to note that the first time we really started to plot stars in what we now call a Hertzsprung-Russell diagram, trying to categorize their properties and understand it in terms of age, was the Hertzsprung-Russell diagram. And it's actually now almost exactly 100 years anniversary since this Nature paper by Russell in 1914 showed how if you plot, in this case he was actually looking at spectral type, but effectively it's color versus magnitude, you see this very well-defined sequence. The stellar properties fall along this sequence predominantly. Of course, it took a while to understand exactly why stars found themselves in this way. I should also point out that Hertzsprung did this also a few years before using star clusters. Russell actually used nearby stars with parallaxes, so he knew how far they were and he knew their spectral properties. But when you look at a stellar group, you actually don't need so much distance information because all that you're seeing is actually at the same distance. So you end up seeing a sequence here, which is actually the main sequence, because the Hyades is actually a young star cluster, so there are very few giants. So even though Hertzsprung, you see the main sequence and you see some giants, here there are very few giants that you see actually in the Hyades. So it was much more of a sequence along a line here, so it's much less detailed. He also plotted it in a different way. This is magnitude versus color, and this is spectral type versus magnitude. So it's quite interesting that this happened 100 years ago, although, of course, we didn't understand the physical reasons for what was going on until much later, when Hans Bethe actually explained how stars form and evolve and get their energy from nuclear fusion. And, of course, this allowed us to take off and really understand this field and use the properties of color magnitude diagrams in order to determine ages of stellar populations. And it goes in a very simple way, just looking at where stars fall of a certain age on this temperature, luminosity, or color magnitude diagram. And you can clearly see how they evolve as they age. So what you see is main sequence stars turning off, evolving into supergiant, supernova. So over a certain time frame, you're starting to lose the more massive, bluer stars. And as you get older and older, you lose more and more of them. At 10 gigayears old, you have this very clear, distinct red giant branch, main sequence of older stellar populations, white dwarfs sitting here. And so if you are able to make these kind of observations of nearby stars, of individual stars, you can pick out exactly what the ages are of these systems and the distribution of ages that you have in a stellar system. So again, this is color magnitude, and all this comes also down to when you look at a further away galaxy, why young galaxies are blue and bright, and old galaxies are red and faint, and it's just the stellar population. And of course, for us as galactic paleontologists, the fact that stars can live a very, very long time means that you can also trace back what happened very clearly in the history of a galaxy by looking at the individual stars and plotting them in a color magnitude diagram and understanding the age distribution that you're looking at. So this is a very famous type of diagram. A lot of work done at the IAC, Aparicio, Gallard, over the years have showed us how you make these kind of color magnitude diagrams, synthesizing the results using stellar evolution tracks, and then you can see how the color magnitude diagram splits into different age populations. So you have here the colors that go along the main sequence that show you that these are young stars, less than 300 million years old, and as you get here, you're getting to older than 8 gigayears old stars, all falling along the main sequence. So if you have main sequence turn-off depth color magnitude diagrams, you can just count the number of stars here and figure out how many stars were forming at different periods in the history of your stellar system. This is just a simple color magnitude diagram to illustrate all the different evolutionary stages. And you can see that if you have the main sequence in a constantly star-forming system, you have an awful lot of detail. And when you look at the red giant branch up here, you can see that all these different populations, older than a gigayear, overlap each other on the red giant branch. Blue loop is mostly young stars, and here you start to have the red clump and then the horizontal branch, which are the older population that you see in a galaxy. And how you interpret this diagram is a lot of work. It's a lot of very careful work to really understand properly how to disentangle age effects, metallicity effects, and a lot of that work is what is being done at the IAC for a range of different galaxies. I'll come to that in a bit. But just to summarize, so what you're doing, you're measuring these colors of these stars, and you're able to pick out different populations. So here's a very unique galaxy, the Carina dwarf spheroidal, where you see these multiple turn-offs on the horizontal branch. And what you're picking out is different age populations in this one small system. Okay? So actually there's thought to be 3 different separate populations in Carina, which give you different ages for these different turn-offs and different numbers of stars that are occurring in the different turn-offs to show you what this galaxy has been doing over the last Hubble time. So how long it's been, what it's been doing for how long. And what I will also talk about today is spectroscopy. So you can also take spectra of the stars, mostly on the red giant branch, just because they're bright enough, where you have all these overlapping populations, and then you can pick out all the individual chemical elements that show up in different resolution spectra. So you can measure the calcium abundance, the barium abundance, how it changes with the ages and with the distribution along these different populations. So this allows you to get metallicity and velocity. And just to connect it to cosmology, what it means that you're doing is you're measuring ages of stars on this cosmic time scale. So you're really looking, you're able, as long as low-mass stars have been forming, you can see them anywhere in the universe if you can find them in our local universe, beside the sun in the Milky Way. We have stars in the Milky Way which presumably formed even in the era when you couldn't actually detect galaxies. If a low-mass star formed, it will still be there today if we can find it. And just looking in a cosmological time frame, you have, of course, the epoch of last scattering. And you have this region, which is the observed universe, which is where we see all the galaxies that we study, all the evolutionary processes we can actually see only in this period here, which, however, is most of the history of the universe. But what we lack is a lot of detail in this intermediate region, this reionization period, when the universe goes from being neutral and opaque to being ionized and see-through, so we can actually see the structures. And from all we know of high redshift galaxies, we see the galaxies very well developed at this point. So at high redshift, redshift 6, 7, you're in this region here, galaxies are already there. Quasars are there with solar metallicity, massive objects. So we know that there's an awful lot of action in here, but it's quite difficult to figure out exactly what's going on. But stars are forming all the way through, as far as we know. So if a low-mass star formed somewhere here, you should be able to find it still alive today with the pattern, with a chemical evolution pattern of what the physical properties were of the region in which it formed stars all this time ago. Now, of course, you also have stars which form and die and shed their chemical elements into the interstellar medium in various different ways. So the picture gets quite complicated to try to disentangle what has been happening on top of what you really want to know, which is the very earliest star formation. So it's not a straightforward measurement to say, I want to find this star. You have to understand how to identify that star by understanding how chemical evolution, star formation, has progressed over time and enriched different regions. So it requires you to understand what kind of objects were you looking at here. Were they small dwarf galaxies? Were they large ellipticals or quasars? How did structure form? And we think we have a fairly good idea of structure formation of galaxies, but we have to try to fit that in with the chemistry that you're actually observing in individual stars and nearby galaxies. Okay. So this whole concept of looking at galaxies star by star is an old one. Galileo started already as many things. In 1609, one of the first things he pointed his telescope at was actually the Milky Way, which until then they didn't know. It was individual stars. And he actually wrote in his paper that you were looking at a large collection of stars when you point towards the Milky Way. And indeed, we now know very well how the back garden looks like. We have the sun in the center here. There are local bubble, which is something like 100 light years across, and you have all these individual stars throughout the local bubble with a range of different properties. So there we have our sun. We know our sun is about 4.6 gigayears old, a G2 type star. You have a nice B1, B2 type star up here, Spica, very young system, 10 to 20 million years old. You have Altair, which is a 7 gigayear-old K giant. Let's have a look what else I put here. Alpha Centauri, 6 gigayears, very close to the sun. Sirius. And you have a whole range of systems with a range of different ages and stellar properties, and you can actually say something about universal properties of how the stars have been forming over this time frame just from looking at our local neighborhood. Okay? It's a hotbed of evolution going over very, very long time frames just on our neighborhood. So we were able to see all these stars very clearly. However, our neighborhood, of course, is not so straightforward to interpret because our neighborhood is moving. Our neighborhood is part of a larger system. When you look at most of the stars around the sun, so now we're talking about, a few tens of parsecs around the sun in a 3D cylinder, most of the stars are moving with effectively a constant velocity in more or less the same direction is galactic rotation. So this is all the stars that you find in the disk. And even looking around in this very small area, there are two well-known stars, Barnard star and Kaptein star, which have been known for a long time to have very high velocities in random directions. Okay, so this is giving us hints that started out as hints that were difficult to understand. What were these very peculiar stars? And we now know that when you disentangle the Milky Way, you have two components. You have the galactic plane, nicely rotating stars, very uniformly moving, and then you have a halo, where you have very fast, chaotic, random motion stars. So it means that when you make a picture of where the stars are in the Milky Way, and we are a tiny dot somewhere in a spiral arm, you can put together all these different properties and try to figure out how you fit in and what kind of stars you're looking at and what has been their evolutionary past. So you can see that most stars sit in the disk, but there are these stars that bounce up and down around the disk with high random velocities that are indicative of different populations in the Milky Way. So even though we look at the sky and we see a huge mix of populations, when you identify these different components, you're able to say something about different components of the Milky Way and to identify them based on their velocity, and therefore to understand how they fit in to the overall evolution of the different stellar populations in the Milky Way. So you can pick out what part of the Milky Way you want to study. And again, the disk tends to be of order 8 to 10 gigayears old maximum, but it also has stars still forming until the present day, because the halo is almost exclusively ancient. If you really want to study the very early days of the Milky Way, you start looking at the halo. So you look at halo stars. This is a very nice movie that was made by Nordstrom and collaborators from the Geneva-Copenhagen survey a few years ago, just showing you the distribution of stars 250 million years ago of this Geneva-Copenhagen survey. But one thing never to forget is that most surveys in our Milky Way are actually of stars that today are around the sun. 250 million years ago, they were spread all out of the disk. But now, everything we observe is actually in a tiny area around the sun. And it's from their velocities that you can figure out where they were in the past, and therefore which component they belong to, how their evolutionary stage has got them to where we see them today in the disk of the Milky Way. And a lot of our galaxies, we struggle to understand it because we're looking within a tiny dot just around the sun. Because if you don't know the distance to the star, you don't know its luminosity, you don't know exactly its position in a color magnitude diagram. So it can be quite difficult. This, for example, are the stars within 100 parsec of the sun, just in magnitude versus color. And it's a bit of a mess, right? Until you put in Hipparcos parallaxes, and then you clearly see that these stars that came from this mess here now orientate themselves, what their absolute magnitudes are, and you get a main sequence, red giant branch, red clump, and you can actually say something about the star formation history of the local neighborhood and the solar neighborhood and the properties of these stars by making comparisons with these kinds of models of how you expect stars of different ages to distribute in a system. And we are about to undergo a huge dramatic revolution in this field because of Gaia. Like I said, so Gaia launched successfully just under a year ago. And up till now, so with Hipparcos, we're looking at this tiny region around the sun. It's a really small region. With Hipparcos, we'll get very accurate distances over most of the Milky Way. So as you can imagine, the difference between this tiny dot and this very large sphere here at the end of the mission will lead to a dramatic improvement in the understanding of the Milky Way. Because now we are restricted to this small area. It's not a terrible restriction, as I said, because stars of all different velocities pass through the solar neighborhood, but it means that the samples are very small. They're going to become very, very big, and it's going to lead to a dramatic breakthrough in our understanding of the Milky Way, which at the moment is limited in many different ways, also including our understanding of streams and all the different properties that you find of the halo of the Milky Way, also of the disk, to understand a little better the formation and evolution of these systems. Because we know within these streams and structures there are a lot of small dwarf galaxies which have not really properly been explained properly, having their properties properly explained and fitting them into the whole zoo of different types of galaxies that you see in the universe. And they are undoubtedly showing a crucial role that is played by merging in the early history of the halo of the Milky Way. How early was it? How big were the structures? Are these remnants of larger structures, or are they intrinsically small and metal poor themselves? A lot of this needs to have a better context for the whole Milky Way, because a lot of them are swamped by the halo of the Milky Way. So until now, we really are mostly studying individual galaxies in the local group. Because the great thing about when you look at an individual galaxy, say Leo A, it's far away, so the stars are much fainter, but all those stars are at the same distance. So the whole problem we have in the Milky Way of disentangling what is where and where it comes from and what may have been its evolutionary path is much less complex. So by looking at these small systems, you actually get an overview of the whole system in a very uniform way. So they're very useful probes. And until Gaia finally finishes its survey, these are the best ways that we have to study these kind of systems, to study a whole stellar system. My particular interest, of course, is to look for the oldest stars, to look for these signs of what's been happening at the very earliest times. But of course, the bigger galaxies are the crucial systems to look at, but these are potentially components that may have gone to build up these larger systems, but at very least they're representative of star formation in the early universe. Because most theories tell us that dwarf galaxies are likely to be very ancient star formation sites in the universe, to get small galaxies formed first. And indeed, as we all know, whenever we take a color magnitude diagram that's deep enough to really distinguish, we always see ancient star formation. There's no indication that dwarf galaxies had particularly different early evolutions than some of the larger systems, suggesting that they're perfectly good representations of how to study what happened in the earlier universe. And we have a very nice range of these different types of systems, from dwarf irregulars, dwarf spheroidals. This is M31. This is a nice dwarf irregular with a huge H1 cloud around it, lots of young star formation. You have galaxies like Tucana, which is no longer forming stars, Leo A, which is kind of forming stars. So you have a huge range of different objects to study individual stellar properties. And you really have a huge power when you look at individual systems. This is Omega Centauri. They're based on HST data, showing you, when you look at a resolved system, the kind of detail you're looking at. You're actually seeing individual stars, and in this case, you can see them move. Okay, you do proper motions. You measure the system over a number of years, and you see how the individual stars are moving. I should point out that the first set of motions are real measurements, and then it's a model, how they're anticipating these stars are going to move over the next 100,000 million years. So you can really build up an incredibly detailed picture of what these stellar systems are doing, and you can then look at the individual stars and see the metallicities, see the velocities, see the kinematics, just try to understand exactly what has been the history. And the simpler the system, in principle, the easier it should be to make a model. And we are still at the stage where the simple systems are proving, first of all, complicated, but also showing us that we really need to have a detailed model of simple systems before we try to build up a very detailed model of maybe more complicated systems. So what can we learn? So we have the most ancient objects of low-mass stars in the universe sitting relatively nearby in the Milky Way in the local group, and we need to find them to study them in detail. Okay? And we understand solar evolution well enough to make stars reliable clocks to track back this evolutionary history of star formation, especially in dwarfs, and especially in systems where you look at a color magnitude diagram and you see something that looks more or less like this. So you have an overall picture of the stellar population of a system where you're actually tracking potentially tens of thousands, hundreds of thousands of stars, but in a system where you can disentangle what are old stars and what are young stars. Okay. And I'm going to talk a bit more. First of all, I'm going to talk a little bit about the color magnitude diagram analysis, but I would also point out that you really need high spatial resolution to do this. And it has been the HST, actually, I think, that has really made the biggest breakthrough in this field by suddenly allowing us to go deep. So sensitivity was important, but also spatial resolution to actually be able to disentangle these complicated, deep images of individual stars. And just to show a simple example from my own work, this was my thesis, a nice, beautiful color magnitude diagram, which partly came from Palomar 5-meter telescope on the ground, a fantastic deep color magnitude diagram of the day, but it looks nothing like the HST color magnitude diagram that came a few years later. And in fact, this is the area that you're probing with this color magnitude diagram. You're just looking at the red giant branch and a little bit of the main sequence here. It's all merged. There's not even the fact that you're not going deep enough, it's also just the fact that you're missing a huge amount of information. And you're trying to make an analysis of a red giant branch which is really not telling you the whole story at all. Okay, so it's very important to get deep and accurate color magnitude diagrams to do this kind of work accurately. You can try, of course, and many people did excellent work, looking at the color magnitude diagrams that you have. And indeed, when we go to more distant galaxies, this is all you have, is true. But you have to remember that this is a detailed and beautiful color magnitude diagram. I just wanted to quickly show a few examples of these beautiful, fairly recent color magnitude diagrams. This is one that Thomas de Boer made of the sculptor dwarf spheroidal galaxy, which is very close. It's 100 kiloparsecs, 90 kiloparsecs away from us. So you clearly resolve individual stars even from the ground. You can zoom in and take a look and see how you're picking out individual stars and being able to measure them very accurately, turn them into a color magnitude diagram. This is a very old system. It doesn't have the young stars. It has a nice horizontal branch, red giant branch main sequence. And from this, you can determine a very accurate star formation history of the system. And as you can see, it lacks completely the young stars. It only has old stars in the system. Beautiful work that's being done here. I hope you've seen it before from the LCID project with the HST. I think this is one of the largest collections that we have of uniformly analyzed, beautiful, deep color magnitude diagrams of nearby galaxies. This is Tucana, for example. There's a whole selection that I sometimes show at conferences with the permission of the PI, just to show that you see this huge range of different color magnitude diagrams. It's all been published by now. It's a program a few years ago led by Karma. And here you can just look at the different types of galaxies and see how different are the color magnitude diagrams. Okay? So you can actually look in tremendous detail going down to the main sequences and determine star formation histories in a uniform way for all of them to understand the physical properties of these galaxies going back to the very earliest times. And there's an awful lot of detail buried in that, which I'm not going to go into at all, but just to say this is the way to try to understand what is important in the formation of these small systems. And one of the most important results is that they are kind of all a bit different. So two galaxies can look very similar in their physical properties, in their mass, and their luminosity, but they will have oftentimes very different star formation histories. But we are restricted to the local group for this, unfortunately. So you can go about a megaparsec away. So this is just giving an idea of the different environments you can probe with the deepest data that we have to date. So if you look at the Magellanic Clouds, HST is almost overkill. You're going way down the main sequence. You're getting a huge amount of detail, usually in a very small fraction of the galaxy. You can look at Leo A. You're getting down to the oldest main sequence turnoffs after quite a number of orbits. And as you go further away, so the 3 megaparsecs, 18 megaparsecs, you can see you're returning to the kind of color magnitude diagrams I showed for Leo A from my thesis that were just showing you red and blue plumes, basically. So we're really quite stuck when you start to get further and further away, and there's nothing to do. These are the most deep data that we have now for these more distant systems. So we really are stuck within the local group. Stuck is not so bad. We have a large variety of things to do in the local group. But just to say, that's the reason that this kind of work is based in the local group. Is that the further away you go, you get problems of sensitivity, you get problems of crowding, but these systems are often very tightly packed stellar systems that as you go further away, they're difficult to observe. And you can very easily figure out how far you have to go, how accurate you have to be, by just looking at how at 1 megaparsec, your distance modulus, the oldest main sequence turnoff is about 29th magnitude in any filter of choice. Horizontal branch is about 25th within this region. So that's why you can see why we're stuck in this region. To go much beyond, you start getting 30th of magnitude for the oldest main sequence turnoffs, or even beyond. And now you're starting to be in the realm of what you hope you can do with very large telescopes, either in space or on the ground. So this kind of work is some of the key motivators for the extremely large European telescopes, is trying to push out this region in which you can actually study individual stars. So you need the sensitivity and you need the spatial resolution. And probably this slide is a little bit out of order. This was just showing two similar mass galaxies where you have color magnitude diagrams of the Sculptor and Leo A. And these galaxies are basically the same luminosity, the same mass, but very different distances. This is almost a megaparsec away, and this is less than 100 kiloparsecs away. And they're having very similar properties, except that Leo A is still forming stars at a small rate, but still having gas, etc. So when you look at their color magnitude diagrams and their star formation histories that come from them, you can see very different properties of two different systems. What's different is their environment. So Leo A has never been close to the Milky Way. It probably sculpture came into the Milky Way a very long time ago. And you can see that sculpture stopped forming stars relatively long time ago and formed most of its stars very early, whereas Leo A formed most of its stars relatively recently. Again, there's always an ancient sign of star formation. And even though in the color magnitude diagram it doesn't stand out very strongly, it's a tiny fraction of the total stellar population, there is a horizontal branch here, and it does contain our Lyrae stars, which shows you that you are always looking at a very ancient population in these type of systems. So all galaxies we observe in this kind of detail do have this ancient stellar population. Now what I want to talk about for the rest of the talk is actually metallicity, because CMDs, even of this quality, do not uniquely constrain the star formation history and the metallicity evolution. It's very difficult to get those two things out of there in a very unique way, mostly because when you go back to the ancient stellar populations, you're talking about very low metallicity systems, and it's quite often difficult to be very sure about what's actually going on. So I would argue you need to measure spectroscopic metallicities and abundances particularly to have a better handle on what's often going on in these early times in these galaxies. So what we're talking about, of course, is chemical evolution, so how chemical elements are distributed in the interstellar medium. We know this happens by very violent processes, such as supernova type 2, which in a dwarf galaxy can have a dramatic effect, can really disrupt the gas, disrupt the star formation, and produce an awful lot of alpha elements primarily, which can distribute in different ways in systems which will change with different times. You also have more quiescent processes like planetary nebula, systems which are just forming stars which are just evolving over a very long time period, having a very small effect. They're not really disrupting the system at all, but slowly but surely you're losing particular processes from the gas which is expelled in these slow-moving stellar winds and these very quiet processes that are going on in a lot of these stars. And then you often see elements like carbon, nitrogen, and S process elements. And also violent, but taking much longer to start, are supernova type 1 explosions, which primarily produce iron. So what you can see is that from looking at these different chemical processes, you can see that different processes occur on different time frames. So this is very quick, relatively quick, gigayear, 100 million, a few tens of millions of years. This is more like a gigayear. This is several gigayears. So you're basically going to have a range of different time scales for these processes, which you want to understand in terms of the chemical evolution history of a given galaxy. So what you end up showing is a distribution of chemistry of different chemical elements and what are their origins. So whether they're coming from internal processes in a star or whether they're neutron capture processes that are occurring during supernova or during stellar winds, you can say all chemical elements in the universe heavier than helium formed within stars through nucleosynthesis. And again, we understand this from pioneering work something like 100 years ago, 50 to 100 years ago. And from that you can just see where all these different chemical elements come from, and the abundances of the gas out of which the sun and our solar system formed 4 billion years ago is represented by this diagram here of the sun. So what we want to understand is the sun different from other stars? Yes, it is. Of course, it's a relatively young star, and understanding how the relative amounts of these chemical elements change depending upon the age of the star and depending upon where you're finding the star. So in a dwarf galaxy, in a spiral galaxy, an elliptical galaxy, you really would want to understand where how these elements are changing, just because you know that they are dependent upon very powerful physical processes that you know can dominate the chemical evolution, the evolution of a lot of these stellar systems, which allow us to understand what was actually the context of physical processes. It's also quite interesting, it's a bit of an aside note, that if you look at the mass of the human body, it's predominantly made up of about 6 elements. You can also compare the elements that you need for life with those that are actually found in the solar abundance patterns that you see. And you can see which chemical elements are crucial for us, obviously, which means for some kind of life. So chemistry, understanding the origin of chemical elements and how they develop over time, has huge implications across many different fields of astrophysics. But how this progresses, what we've been doing in the DART project, this is something that the DART team that I mentioned at the beginning has been very active in doing, is doing spectroscopy of these galaxies with relatively well-determined or possible to determine very accurately detailed star formation histories. And we look at the red giant branch. Conveniently, the red giant branch contains basically between 1 and the most ancient gigayear-old, 1 gigayear and the most ancient stars that you'll find in these systems are to be found on the red giant branch. And you can pick them out for spectroscopy. They're also the brightest stars, so it's convenient with the fact that these bright stars also cover a very large age range in the history of a system. And you can pick them out individually, and we're very fortunate to have the FLAMES multi-fiber spectrograph on the ESO VLT that came online about 10 years ago and has allowed us to do large surveys of different types on these systems. So the first type of survey is a low-resolution spectroscopy, which is Giuseppina's speciality, which is looking at indicators for the chemistry. You also get velocities from this as well, and you can then determine metallicity distribution functions of a range of different nearby systems. So we're still not able to go very distant with this because the stars are relatively faint in the color magnitude diagram. And you can look at, for example, in this diagram, which comes from Giuseppina's thesis, is showing you the high metallicity stars are in red, and the low metallicity stars are in blue, just split along this line here, so high and low. And you can actually see just by eye that the kinematics are different of these two systems. And that's quite a dramatic result. In a tiny dwarf spheroidal system, the fact that you see these two distinct components that you see in velocity, metallicity, and also in the properties of the horizontal branch shows you that you have a very complicated system. And you can use them to determine very sophisticated mass models and try to understand how the evolution of this galaxy came to this point. This small, simple, relatively simple system is not so simple after all. The other thing you can do also with FLAMES is to go to intermediate resolution spectroscopy. So the previous diagram was 8,000, a resolution of 8,000. Now we're going to about 20,000. And you can start to pick out a number of different chemical elements, which then allows you to determine things like the relation between supernova type 2 enrichment and supernova type 1a. This very classical knee, which you expect to find, and you do find in the Milky Way, for example, showing the difference between high alpha abundances and low alpha abundances, just showing a period when there had not been supernova type 1a, and here when supernova type 1a start to contribute very strongly in a system. So supernova type 2 have fast enrichment, supernova type 1 much slower, longer-term enrichment. And what you get is this classic diagram. There's a compilation of data by Venn. It's getting a little old by now, but more or less, even new surveys look something like this, where you can see this plateau at very low iron abundance in the halo of the Milky Way. And here you have the disk at much higher lower magnesium, at higher iron abundance here. And people have classically drawn on top of that this knee. They've shown this as an example of the fact that the halo is old, the disk is much younger, so you're ending up with, here you have primarily supernova type 2 enrichment, and here supernova type 1 and 2 are important. And the thing that we contributed as a DART survey is actually looking at these detailed properties of, for example, an alpha element, magnesium, compared with the halo. And one very interesting result is that it's very different from the halo. So the sculpture dwarf spheroidal in the alpha elements looks like this. The distribution is like this. So it doesn't go to very high metallicities, but you can see that the knee, the position of this transition, is actually shifted, right? So when you look at the sculpture dwarf spheroidal, you're seeing this knee occur before in a lower iron abundance than you're seeing in the Milky Way, which is telling you about how rapidly physical processes are occurring in dwarf galaxies compared with a structure like the halo. So the halo has had much higher, much faster chemical enrichment before actually supernova type 1 started to occur, which is telling us something about the different physical conditions in the early times between the halo and the sculpture dwarf spheroidal. And when you look at this as a survey of the different galaxies, and Sculptor is the galaxy we know the best. This is the Milky Way in the gray points, Sculptor in green. These are the two knees I just showed. We also have various somewhat incomplete studies of Fornax, Sagittarius, and Carina. And broadly speaking, you start to see a pattern where you see that the knee appears to change as you go to smaller, fainter systems, suggesting tentatively that larger systems are actually able to enrich more with supernova type 2 before the supernova type 1a start to take over. Okay. You can also look at the very low metallicity end of these dwarf galaxies, and this is again where I'm particularly interested, because you're really starting to hopefully probe the very earliest periods in the universe, understanding the very metal-poor populations that you have in the sculpted dwarf spheroidal, which is one of the best studied with spectroscopy galaxies that we know of. And you can see that you get a star at -4. That's the most metal-poor star that you have in these dwarf galaxies. And if you compare it with, for example, the Carrel sample of halo, you can see that it's not so different. You could argue that it seems that sculpture has a higher scatter, so a higher amount of distribution, variation of the alpha element than you actually get in the halo. But broadly speaking, you're saying that the older populations may actually be quite similar between these two galaxies. It's something that requires more detailed study. And one piece of work that I think has been quite provocative in this field is the thesis of Thomas de Boer, who basically took, for the sculptor galaxies, now worked on several other galaxies as well. So we have all this imaging, all this spectroscopy. So we have a nice color magnitude diagram with the star formation history. We have this chemical evolution, all this abundance information going to the very metal-poor stars, to the most metal-rich stars. So we know the metallicity distribution function quite well. And we also have individual abundances for a large number of stars. And then the thing is to put it together. So you have color magnitude diagrams which give you ages, spectroscopy which doesn't give you direct ages, but it does give you metallicities, and you try to combine those two information. And that's one of the first times it was actually done. And I find it quite interesting that actually the color magnitude diagram fit he got without the spectroscopy was much better than the one he got with the spectroscopy, which I find comforting, because it means in some sense that you're adding information and it's showing you the problems that you have, making straightforward assumptions when you can't actually measure them. So we know that there are issues with stellar evolution tracks. We know there are issues with exactly how you uniquely disentangle what's going on. But when you add this spectroscopic information, you end up giving more information to a model and having to understand a bit better what the errors are and the uncertainties are. And you end up with a slightly different, it's not hugely different, I have to say, but it means that there are subtleties that play a very strong role in having more information, of course, which allows you to build a more sophisticated, better model. And one of the results of this is you can take the model, which are the small dots here, and put on top of the model the spectroscopic observations, where you have detailed chemical abundances of these individual stars. Here it's just plotted with the iron as a color. So you can broadly see that the color you're having of the spectroscopy is more or less matching with the model, which then means you can pick out the stars that you're measuring and give them a very accurate age tied in with the star formation history that you're actually determining from the color magnitude diagram using. So it's not entirely, it's a bit circular argument, but it means that you're making self-consistent ages and with star formation history and with the chemical abundances of these individual stars, of the iron abundance. Then you can, for example, look at these stars. So these are measurements now where the ages have been taken from the star formation history. And what you get here is ages going from older stars to younger stars, showing you how the magnesium abundance is changing. And again, this has always been an assumption, of course, that alpha elements are produced first and then they start getting supernova type 1 abundance. So actually to measure the time difference between the stars which are only enriched by supernova type 2 and those which have a strong component of supernova type 1 is a very interesting result, to actually measure it directly. There's no model assumption particularly going into this. It's just showing, so relative terms, there shouldn't be any problems here, telling you the time difference between what's going on here and what's going on here. And it's interesting that the chemical enrichment of Sculptor, it took about 2 plus or minus 1 gigayears for the supernova type 1 to really kick in, which is slightly longer than is predicted from theory, but most theory is relating to very large systems like elliptical galaxies. So it's broadly consistent, and it may not be surprising actually that dwarf galaxies again take slightly longer in order to get to the stage where they can actually look at supernova type 1 enrichment. And again, Thomas has now gone and done this for a couple of other galaxies. I find Sculptor the cleanest example, because these other two galaxies have complicated star formation histories. They have intermediate populations on top. Here you're looking at a pure old population. So here you're really able to see this without the complication of trying to understand which components come from where and what lies on top of what in these different systems. Okay. So I'm basically just going to talk a little bit about looking for the signatures of the first stars when you start to have high-resolution spectroscopy. you can also start to try to figure out what might be the properties of these stars in the very early universe, measuring detailed abundances of neutron capture elements, for example. And one of the overriding results of the last 10 years has been it's very hard to find a star which looks like the models that people are making of first stars. We don't find anything with the chemical evolution patterns. The red dots are the Carrel measurements. These underlying black lines are models, standard supernova type 2 explosions, a special zero metallicity star supernova explosion. Then you basically don't see the signature that you would expect of as first star. And of course, there are various reasons for this. People don't completely understand why it should be. It could be the fact that you're actually looking at a top-heavy IMF, meaning none of the remnants are still around today. But one result that remains there is looking at the carbon-rich stars. So a very large fraction of metal-poor stars in the halo have very high carbon abundances. Right? So this is now seen to be an indicator of some early process that is going on at the very earliest times, which is enriching the carbon. So when you look at the neutron capture elements, the heavier elements here, more or less you can fit them with some kind of standard model. The red dots are the measurements, and these are the models. But when you get to the carbon, you can get extremely high carbon abundances, which you cannot fit into any kind of standard model. So the idea is that they're telling us something about an intrinsic process which is going on very early in the universe. It's producing an awful lot of carbon. And there are various ways of trying to do this. But one interesting point that I would just want to quickly make at the end here is the fact this is the halo. The halo is very well studied. They've made a lot of effort to try to find these very metal-poor stars. They have these very comprehensive statistics. But when you look at dwarf galaxies, you see quite a different story. That when in the halo you have a large number of carbon-rich stars at low metallicity, you seem to miss them in dwarf spheroidal galaxies, which remains a bit of an issue, because why should dwarf spheroidal galaxies be different from the halo? Why should you expect to see a large number of carbon-rich stars in the halo and not in dwarf galaxies? And indeed, we've done careful studies, for example, with Sculptor, looking at the most metal-poor stars in Sculptor. We didn't find any carbon-rich stars in these systems at all. However, this is a nice result coming from Ausa Skuladotter, who should get her thesis at the end of next year, where she did, just by chance, she found stars which had very strong CN lines in the Sculptor. We were looking at a completely different wavelength range. We were looking for sulfur in the 9,400 angstrom region. And these are actually the result of the CN estimates of these stars. And we found this one star that stuck up very strongly above the rest, showing it's mildly carbon enhanced. But you can clearly see it's very different. But it's at a very high metallicity. So this is something we're still working on, trying to understand what this star could be and how it fits into our understanding of carbon-rich stars in the halo versus what you're seeing in dwarf galaxies. And this is some modeling that's being done by Stefania and Ausa, where you're actually making a model of what you think is the star formation history of the galaxy, which you know. They can reproduce the metallicity distribution function in iron, and this gives you a prediction of how many carbon-rich stars you should find in which metallicity range. But because the galaxy enriches so fast, actually the probability that you have of finding a carbon-rich star is actually larger at higher metallicity here. So perhaps it's not surprising that you're actually picking out these carbon-rich stars at slightly higher metallicity. They can still be tracers of the early evolution of carbon, and so forth, also for the earliest star formation in these smaller systems. But maybe we have to start looking at higher metallicity in order to get the full picture of what exactly is going on. I just end my talk by looking to the future. Again, I know IAC is involved in harmony, still I presume, and I think this is going to be an extremely exciting era for stellar population work as you get to bigger telescopes where you can make very detailed color magnitude diagrams and hopefully also take spectra of these individual stars much further away to really push our knowledge beyond the local group, because the local group is local, it is limited, and this is something that would allow us to look at a larger range of environments, specifically looking at elliptical galaxies. Because up till now we're really looking around a spiral galaxy, around a rather small, weak group. But everything, we have already established techniques. So we know exactly what has to be done to observe these stars, young and old, and put them into different contexts and compare them in detail with the environment of the Milky Way. So that's my talk.
Thank you very much, Eline. Questions?
I remember a while back these extremely metal-poor stars in our halo were thought to be binary, or at once binary.
That's correct.
So the question arises whether the binary fraction might be different in sculptural and dwarf galaxies. And then the question arises, can you see binaries if you're looking at individual stars? And there's some logic to think it might be, the binary fraction might be different in different star formation environments.
What I didn't really manage to go over because I was running a bit out of time is that the stars I'm actually talking about are the CEMP no stars, which have been shown in the halo not to be binaries. They're not no. That's, I mean, we can't prove that, of course, but yes, of course. No, but usually you get S-process elements. You get very strong signatures of barium elements like this, which you do see in CEMP S stars. But it's a different class. So what I'm actually talking about both in the halo and in the dwarf spheroidal galaxies is CMP no star. And they've been doing careful studies now. There's a paper, I think this year, by Starkenberg, where they're looking still for binarity in these very metal-poor, carbon-rich no stars in the halo, and they don't find any signs of binarity. So it's believed that I mean, there is certainly a path to enrich the carbon with binarity. It's clear with mass transfer. But they have very strong S-process signatures. And there are large numbers of those stars, too. But they're not what I'm talking about here.
So you showed a plot, I think it was a sculptor, where for the most metal-poor stars, the magnesium over iron ratios are actually, they look more like kind of the disk magnesium over iron ratios to me than would you expect for the halo. I mean, they were quite... Okay, I'll wait for you.
This plot?
They were quite low? Or, I mean...
Previous or...
yeah, maybe. Well,
this one? See if I go.
Yeah. So, I mean, is that expected that so iron on over hydrogen minus kind of -3, -4, they kind of seem to creep down towards.
It's a surprising result indeed, and that's what's coming also when you're comparing the very low metallicity stars that suggest there may be a higher scatter, because of course the number of stars you have in sculpture at that low metallicity are really small. And they're difficult to measure because they're further away than most of the stars in the halo. So there are certain experimental uncertainties that maybe that you do not expect that, no. So it's a bit surprising, and we've wondered about what it could be. And there are other samples of other galaxies where you also see very low magnesium at low iron in dwarf galaxies.
Very interesting.
It is very interesting.
Thanks. To what extent the fact that these stars have crossed the galactic plane many times along their lives, could they have accreted material that changes the ratios, the primordial ratios?
Could always be. I think it's quite hard to accrete material onto a star. It's like a bullet moving through a cloud, as far as I understand. They're moving so fast through the disk that it's very unlikely they pick up material. People have been doing studies trying to understand if this could happen. There's a paper by Venn et al., I think, with Lambert somewhere in there, and they're basically trying to understand. They're actually looking also for dust characteristics that would show if there was an interstellar medium around, or if it would be somehow you could explain this. And so far the result has been negative, but it's complicated to make that kind of measurement and to try to really see that. Typically you would expect abundance ratios which are very different. So whenever you pick up interstellar medium, you would expect the abundance ratios to have mismatches between, for example, what you're looking at and what we're seeing in the most of the star, which of course you are seeing. It's a carbon mismatch. But so far I understand it's very difficult to understand how to pick up the material and how to do it without really leaving a signature of this in some way. But
in one of your slides, you made a blanket statement saying small galaxies formed first.
yes.
Is there any real evidence for this? I understood that this is quite controversial, in fact, and that if you look very carefully at ages and metallicities and so on, the situation is much more confused.
I agree. No, it's a fair comment. I mean, I say it in this, what I really mean is that there's no evidence that they have strongly different, because a lot of times in the past people said they must have formed later, they're smaller, they're low metallicity, everything must have happened, but much later. Some of the work being done here, you're seeing signs that there are differences at the very early times, but not dramatic in the sense, it's not like an absence of something, it's just maybe the rate at which they're forming stars, starting to form stars is slower. They always have ancient star formation. So there's no reason to think that by studying dwarf galaxies, you're somehow not studying the earliest populations, is what my point was trying to be.
Okay.
Rather than.
Thanks.
Yeah, connected to that, the star formation histories that you can explore here in a lot of detail. So, are there any signatures on this star formation history connected to regionization? So that
connected to what?
Regionization. So that you see that the old star formation is.
That's more my colleagues here in the IAC can maybe answer that. I don't know. I mean, Sebastian did some of that.
There is no signature of reionization stopping the star formation history in this galaxy by now.
It's very hard to be sure, for sure, because you're talking about a very short time period, very early on, but there's no evidence for it.
Yeah, this plot here, and another one where you showed that this turn down occurs at a different metallicity for different masses. So I suppose the turn down occurs after a gigayear. So you have a different metallicity of a gigayear-old galaxy as a function of mass. So that's the same as the mass-metallicity relationship that's observed at redshift 1, which we know has that relationship.
Interesting. Okay. Maybe it's not surprising, but we're talking about magnesium here.
But there's this clock.
Yes.
And you see the iron after
the way it's going.
We know what redshift that is. It's equals 1.
But I suspect when you're looking at redshift 1, you're looking at much bigger galaxies than this. So,
there's a mass metallicity
yes, I agree.
Going down to, I think, 10 to the 9th school in that.
Okay. I don't think I'm anywhere near 10 to the 9th with these galaxies. These are really small, but still, no, it's interesting. Because usually when you look at, for example, Tremonti mass metallicity relation and you extrapolate to the local group, you don't find it's not really consistent. So I think there are some issues there. But broadly speaking, you're right. That's what we're seeing.
Last two questions.
Okay. You hadn't talked about this thing, but are there any hint of very low metallicity, very young star?
Very low metallicity, very giant star.
Very young.
Young. Low metallicity. Yeah. Well, what do you call low metallicity? Yes. I mean, 1 Zwicky 18 is 2%.
10 to the minus 3 or...
1 Zwicky 18. So, for example, 1 Zwicky 18. In the galaxy,
the individual stars of 1 Zwicky 18...
2% solar.
It's more than that. So it's... Yes, a few percent solar. So the individual stars of 1 Zwicky 18 are younger than 1 gigayear?
Yes. Well, yes. These massive
and
stars.
Lower?
Because they're H2 region metallicities, typically.
And lower metallicity and younger?
That's not... I think that's the lowest metallicity galaxy we know about by quite a margin. There's not very many galaxies in that category. And when we say it's 2% solar, you're measuring it from an H2 region, which means by definition...
No, but I'm talking about stars. So that's my question was specifically about stars. I know that 1 Zwicky 18 has a gas which is very metal poor, but I'm talking about stars.
Yeah, I'm talking the 1 Zwicky 18. They measure this metallicity in the H2 regions, which means they're measuring the massive stars, so very young stars.
No, but I'm talking about evidence directly inferred from the stars. So you know of a specific star with this low metallicity and young? Not the H2 regions.
I think so. I mean, I think their H2 regions are the individual stars, and they are resolving them very well in 1 Zwicky 18. So there are individual stars, but then to get a spectrum of that individual star for an ELT, it's something, because they're a bit too far away. And there are very low metallicity, like Leo A is very low metallicity, but doesn't have very massive stars. So it's got stars that are probably of order 4 or 5 solar masses, right? So they're still quite young, but they're not that low metallicity.
Okay. Is there information about the same diagram in dwarf irregulars?
Not with this kind of detail.
Way?
There is actually in the review in Tolstoy et al. 2009 from the work, I think, of Kim Venn predominantly, where she did look at, but then again, massive stars. So you're looking at the end product. So you're looking at A-type stars, typically. And then you're seeing the end product. So you're actually seeing low alpha at relatively high metallicity. So, but they're never going to be in this detail because you're not able to get the red giant. This is from red giant branch spectroscopy, and you can't do that quite for dwarf irregulars with this kind of accuracy. I mean, Giuseppina is trying with dwarf irregulars a bit, but not really to get alpha elements. You would like it, but I mean, it's something people are trying, but it's a very challenging project. And maybe you'll get 1 or 2 stars, but it's very unlikely you'll get. Maybe you will over time.
Okay, so Eline will be with us today, tomorrow, and Monday morning. And you can find her in Antonio Aparisio's office here in the first corridor. So before moving to the science coffee, let's thank Eline again, please.